Hey you! After talking about programs and functions in our last 3 videos, it's now time to focus on function blocks.
For this purpose, we have come up with a nice scenario that we will introduce to you in a minute. And there will also be a complete TwinCAT project available on our GitHub. You can find the link in the video description.
This is the first of 2 videos we created for the project. In the video, we will go through this project step by step together and demonstrate and discuss concepts of object-oriented programming.
In the project, we deal with the following situation. We have 2 monkeys that need to be pleased and treated well. Our goal is to satisfy them with candy that they will get from a vending machine. Each of them will get their own machine.
On the one hand, there will be no argument in front of the machine, and on the other hand, the 2 have different behaviors when it comes to enjoying sweets. One of them is greedy and one is picky.
The greedy one is, of course, Enum, and the picky one is me, Ajnan. Enum is easy to satisfy. His satisfaction level rises the more sweets he eats.
Because Ajnan is the picky one, she separates the candy types in disgusting, okay and delicious. If she eats a disgusting candy, her satisfaction level falls. If she eats an okay one, it's neutral, nothing happens, and if she eats a delicious one, the level of satisfaction rises. Our TwinCAT project will include all of the elements you have just seen. The monkeys, their level of satisfaction, the elements that calculate their satisfaction, candies that are classified into different types, machines that contain them, dispatchers, suppliers, and so on.
To demonstrate how everything is structured, we have designed a diagram that can serve as a blueprint for us.
You can find the entire diagram in the GitHub repository.
This part of the diagram is relevant for the first steps in the video.
In the first part of the video, we will create an AnyToArg converter. The data type any will be converted to the data type arg. We will explain why we need it in a minute.
We will also define an abstract class for the candy, an abstract class for the CandyDispatcher, and one for the CandyConsumer. And create some types that are relevant to these classes.
First, let's focus on the converter.
Let's start. At first, we create the TwinCAT PLC project and clean up the folder structure. Now we increase the max stack size to 4096 KB, because more is better. Hey. We want to log the candy consumption. Therefore we will use a FB out of the TC2 utility library. We add the library. The FB we will use is the FB format string, which is much easier and more convenient to use than TC2 standard concat. This function block can be used for converting up to 10 arguments into a string. The output string is, for example, immediately available after the FB was called, because the formatting occurs in the same PLC cycle.
After we prepared this, we will create our first class, which will provide an converter. That's why we call it AnyToArgConverter. This class will convert from any type to the type tc2utilities.targ.
The any type is the same as system.anyType. Any is a generic data type for input parameters and can't be assigned to constants. Any always needs a variable as input, because a pointer to the actual value is transferred and therefore you need a memory address. TArg is an argument type for string format functions and function blocks. TArg is the predecessor of any.
Any was defined in the IEC 61131-3.
Because we want this to be an abstract class, we check the box next to abstract.
In our newly created class we can find the keyword abstract now. The abstract keyword is available for function blocks, methods, and properties. If you want to implement a PLC project with abstraction levels, this is your keyword. But what is abstraction?
Abstraction is a key concept of object-oriented programming. You have one abstract basic class, which implements basic functions and properties. Specific aspects can be implemented in concrete subclasses. The following scenario illustrates the usefulness of abstraction. By creating an abstract class called vending machine and having both the pink vending machine and the boxing glove vending machine extend it, we can ensure that they both have the basic functionality that any vending machine should have. This means that any code that is written to interact with a vending machine can be used with both machines, regardless of their unique characteristics. Similarly, the monkey in this scenario demonstrates the benefits of abstraction in real-life situations. By understanding the basic concept of a vending machine and how to use it, the monkey can interact with any vending machine it comes across, regardless of its color or how the candy is dispensed. This means that the monkey is not limited to only using one specific vending machine and can easily adapt to new environments and situations. If the monkey were only able to use one specific vending machine, it would face difficulties if it had to move or if that specific machine was not available. Back to our abstract keyword in TwinCAT. An abstract class is used as basic class by inheritance because it cannot be instantiated. An abstract class can also contain non-abstract methods or properties. If you use abstract methods or properties, they only can contain declaration, no implementation.
If you use them, the FB, which contains them, also needs to be abstract itself. And abstract classes must be extended in order to be able to implement the abstract methods or properties. If you use a derived class, it must implement the methods and properties of the basic class, or it must be defined as abstract.
You said an abstract class is used as basic class by inheritance. While we are at it, let's talk about inheritance.
Okay, inheritance is also a key concept in object-oriented programming, and it's super useful, but it can be tricky to grasp at first. Let's break it down.
At its core, inheritance is a way for one class, called a child or subclass, to inherit the properties and methods of another class, called the parent or superclass. It's like getting a blueprint from your parent class and building on top of it.
Exactly. For example, let's say we have a vehicle class. It might have general properties like speed and fuel. Now, if we create a car class that inherits from vehicle, it gets all those properties for free. But we can also add new stuff specific to car, like number of doors.
You use inheritance to avoid repeating code. By placing shared functionality in a parent class, you don't need to rewrite that functionality in each child class. The child class just reuses it. It also helps organize your code by grouping related things.
Right, think of it like this. If you've got multiple classes that have things in common, like car, motorcycle and bus, instead of copying the same speed and fuel stuff into each one, you put that in vehicle, and they all inherit from it. Makes things way easier to maintain.
Now, abstraction takes inheritance to the next level. An abstract class is meant to be a blueprint that other classes follow. You can't create an object directly from an abstract class, it's too vague. But you use it to define methods that must be implemented in the subclasses.
Imagine a shape class. You don't know what specific shape it is, but every shape has an calculate area method, right? You'd make shape an abstract class, with an abstract method calculate area. Then, classes like circle and rectangle would inherit from shape and implement calculate area in their own way.
That's the is-a relationship. A circle is a shape, a rectangle is a shape. But each one implements calculate area differently, based on their own unique formulas.
Now here's where it can get confusing. Sometimes we extend a class not because it represents a true abstraction, but just to borrow some functionality. Let's say you have a utility class, math functions, with useful methods like add and multiply. You might extend it just to use those methods in another class.
Right, but extending a class for functionality isn't about the is-a relationship. You're not saying your class is a math functions, you're just borrowing its methods. It's like adding a toolbox to your class, not saying your class actually represents that toolbox.
Exactly. For example, if we have a class like AnyToArgConverter that just provides some utility methods, you might extend it just to get those methods. But you're not using it as a true abstraction, it's more like adding functionality on the side.
Let's have a look at the key differences. True abstraction, abstract classes. Represents a blueprint. Defines what the class should do but not how. Cannot be instantiated. Forces subclasses to implement abstract methods. Extending for functionality. You extend a class just to use its methods or properties. It's not about the is-a relationship. You're borrowing functionality, not abstracting behavior. So, to sum it up, inheritance is about sharing functionality between classes, while abstraction is about defining shared behavior that each subclass can implement in its own way.
And extending for functionality is just a shortcut to reuse methods, but it's not the same as true abstraction. You're using the toolbox, not becoming the toolbox.
That's the difference. Keep it clean, use inheritance when it makes sense, but don't mix up abstraction with just borrowing functionality.
Now that you know more about abstraction and inheritance, let's go back to our TwinCAT project. The abstract class we created will provide just functionality that can be used by inheritance.
It won't have public methods. There will be just one method called AnyToArg accessible for the child class. This method will be final because no one should overwrite it.
We create this class because it is much more convenient to use one method to convert, for all cases, than the tc2utilities.fbyte, tc2utilities.fword etc. functions provided by Beckhoff.
Some of you are probably wondering what we are talking about, using words like private and final when talking about methods.
And also methods, we haven't talked about them in detail too.
Don't worry, we'll do that now.
Therefore, we will create our first method. Click on the class, select Add and click on Method. At first we can give the method a name. We call it TypeClassToArgType. If you click here, you can select one of the following standard methods. FBInit, FBExit and FBReinit. If it is a derived FB, the list will also offer all methods of the basic class. As return type we select tc2utilities.yardType. Like functions, methods can return a return value. Next we can select an access modifier. With this modifier we can regulate access to the data. By default a method is public. If you select public, the access is not restricted. For our method we will use the access modifier private, now the access is restricted to our class respectively. The next modifier is protected. If you select it, the access is limited to the program or function block and its derivations. If you select internal, the access to the method is limited to the namespace / the library. There is one other modifier, which can be added in addition to the access modifiers. Final. If you add final to the method may not be overwritten or extended in a possibly existing subclass. Now, we can select if our method should be abstract. We don't want it to be abstracts, that's why we don't check the box.
What else do you need to know about methods? Data within a method is temporary and only valid during execution. TwinCAT reinitializes all variables and function blocks declared in the method for each call. You can declare varianced variables to ensure that methods do not reinitialize variables. TwinCAT generates varianced variables for methods, which are not located on the method stack similar to var variables. Instead, they are placed on the stack of the function block instance. Like functions, a method can have additional inputs and outputs, and you can declare varanouts. Note, from TwinCAT 3.1. 4026, inputs without an explicitly specified initial value must be assigned when the method is called. Inputs with an explicitly specified initial value can be optionally assigned or ignored when the method is called. Access to the function block instance or program variables is allowed in the implementation part of a method.
If you want to call a method, you do it like this. If you also want to assign extra outputs, it looks like this.
Sweet.
Now that you finally know more about methods, let's go on with declaration and implementation.
The method we created will translate the system.type class from system.anyType to tc2utilities.argtype from tc2utilities.targ. At first, we declare the inputs. Type class of type system.type class. This is the type class to translate. The other input is called size of type uint and will be the size to determine the base type. Next, we declare 4 constant variables for the different lengths of the base types. In the implementation part, we implement in case of instruction, which converts certain types of system.anyType to the corresponding data type of to tc2utilities.argtype. We will speed up this part and recommend you to download the project if you didn't do it yet to follow along. Magically, we filled our case instruction with all these data types. Look. For subranges and enums, we use another case instruction. At the end of the instruction, we use an else. If the type is unknown, we will get back tc2utilities.argtype. Argtype unknown.
We create another method and call it AnyToArg. As return type, we select tc2utilities.targ and as access specifier private. This method takes a system.anyType type and returns a tc2utilities.targ of it. Therefore, we declare an input variable called in of type system.anyType. When compiling the code, the input variables with any data type are replaced internally with the following structure. The structure elements are assigned to the actual call parameter at runtime. Type class of system.type class, this is the type of the actual parameter. Value a pointer to byte, this is the pointer to the actual parameter. D size of type dint, this is the size of the data, to which the pointer points. In the implementation part, we convert the different parameters. In the last line we write AnyTypeToArg.eType equals this .type class to argtype, in .type class, AnyTypeToArg.cblen.
Here we use a dereferenced this pointer. This is the pointer of a function block to its own function block instance. You can only use this inside a function block. A this pointer can be used if a function block variable is shadowed by a local variable within a method. The this pointer can then be used to access the function block variable. The this pointer can also be used to assign a pointer to the own FB instance with a function call. We use it always, for better readability.
We also need a method for dereferencing any types until it find a non-any type. That's why we name our next method dereferenceAnys. It is also private. This method is recursive. That's why we use the estimated stack usage attribute in the method and set it to 280. The pragma transfers an estimated value for the stack size requirement. Methods that contain recursive calls cannot pass a stack check as it is not possible to determine the stack usage. Therefore, a warning is generated for these methods. To avoid this, we use the attribute. We declare an in variable of any type to dereference it. It's called in. As output, we will give back the dereferenced system.anyType and just call it out. In the var section, we declare an pointer to get the next address. We implement a case instruction to dereference the any type until we get its real type.
The last method we add is the AnyToArg method. As return type we select tc2utilities.targ. As access specifier we set protected. And behind protected we manually add final. The method AnyToArg is final because no one should overwrite it. This method takes an any type as input parameter and returns a tc2utilities.targ of it. We declare an input variable called in of type any. This will be the data which should be casted to tc2utilities.targ. As second variable we declare data of system.anyType. It will store the any without changes. In the implementation part we write data.diesize equals in.diesize. Data.pValue equals in.pValue. Data.typeClass equals in.typeClass. This .dereference any's in equals data, out equals data. We send the data to our dereference any's method and get the dereferenced data back, which we can now send to the AnyTypeToArg method. At the end, we get back our arg type.
Because we like clean and clear projects, we add two folders. One for the private methods and one for the classes. The next thing we will do is to create an enumeration. For this we create 3 more folders in our project, so that we can store our types neatly. Next we create an enumeration. In here we will store the candy types. That's why we call it CandyTypes. We remove the attribute strict, because a suite usually consists of a mixture of different types. A single bit represents each candy type. The candy type is stored in a word, means there can be 16 different candy types. Each suite can save its type by setting the corresponding bits. For example, is a Snickers a caramel candy, a candy bar and chocolate candy. That's why a Snickers has the value 16 #0019 because we can say a Snickers is candy bars or caramel candy or chocolate candy equals 16 #0001 or 16 #0008 or 16 #0010 equals 16 #0019. Natural language would say a Snicker is a candy bars and a caramel candy and a chocolate candy. Next we will create a folder for 2 alias types. The first one we call CandyName. As base data type we select tc2system.tmax_string. The other one is called CandyAmountInGram. As base data type we select uint with a subrange of 0 to 500. It's used for the candy amount. The candy machine is able to handle packaging units up to 500 grams. We created the 2 alias types to be more flexible. It is easier to change the base data type than to change a data type everywhere. For example, if our candy machine can also handle big packs up to 1000 grams, we can just modify the base data type. There is one more positive effect. An alias with a specific name makes it easier to find what deals with the candy amount. We have just to search for CandyAmountInGram instead of uint, which is very unspecific.
Now it's time to create another abstract class, and this is our first abstraction. First, a folder for the classes. Next, the class itself. We call it AbstractCandy. It is an abstraction layer for candies and every candy must inherit from it. As variable we declare candy type, name and amount. Next, we will add 3 new properties. Therefore click on Add and select Property. We call the first one, Amount of Candy with the return type, CandyAmountInGram. You also can define an access specifier for a property. Also, the getter and setter can have access specifiers. You can select between the same specifiers we already explained to you when we talked about methods. And a property can also be abstract. A property consists of 2 accessor methods. TwinCAT adds them automatically below our property. One is the get and the other the set accessor method. The set accessor is called when you need write access to the property. For example, when you use the property name as input parameter. The get accessor gives us read access to the property. When you use the property name as output, the get accessor is called. You need to implement the accessor methods to have access to the property. If you only want to allow one of the accessors, you can delete the other one. A property can have local variables, but in contrast to a function or method, it can't have additional inputs or an output. Our property needs just a getter for the candy amount. We implement it like this. Amount of candy equals this dot amount. We call the next property, name of candy, and as return type we declare CandyName. This property also just needs a getter, and will return the name of the concrete candy like Snickers or Alpenliebe. We delete the set accessor and implement the following line in the getter. Name of candy equals this dot name. The last property we need is one that returns the type of the candy. We name it type of candy, and as return type we assign our non-strict CandyTypes enum to it. We delete the set accessor. In the implementation part of the getter we write type of candy equals this dot candy type. Right now the class has just 3 properties and looks like a data transfer object. But we will extend more functionality later.
Next we create a new folder and call it CandyConsumer. Another folder called Types. And one that we call Aliases, because, for our Candy consumers we want to add 2 more alias types. The reason why we use aliases is again flexibility and better navigability. The first type is a tmax string alias for the consumer name. The second one is an alias for a nuance subrange from 0 to 100. It is used as satisfaction level for the Candy consumer. 0 means depression, 100 means euphoria. Now that we created the types for our Candy consumers, let's go on with a class for them. Let's have a quick look at our diagram. We will now create the class AbstractCandyConsumer. It has for each candy type an eat method, a satisfaction level and a name property. Here we have the first abstract methods and properties. That means if a class inherits from AbstractCandyConsumer it must implement them. Back to our project. We call our class AbstractCandyConsumer. This class can eat candies and the class will affect the satisfaction of the consumer. That's why we declare a variable named satisfaction of type SatisfactionLevelInProcent. Next we add abstract methods for each candy type. Let's do the first one together. We call the method eatCandyBars. As var input we declare a variable called amount of type, CandyAmountInGram. It represents the amount of candy that the consumer eats in gram. Now we add such an eat method for every candy type. Always with the same declaration. The next thing we do for this class is to create a property. We call it level of satisfaction with the return type, SatisfactionLevelInProcent. We delete the set method. The getter is used for the actual satisfaction level of the consumer in percent. To get this we implement the following line. Level of satisfaction equals this dot satisfaction. The next property is abstract and we call it name with the return type, ConsumerName. As you can guess, it's the name of the consumer. Haha. Again we delete the set accessor. The getter we need for logging purpose. We leave it as it is and go on. Let's have a look at our diagram, and tell you what we have in mind. Next we will add the class AbstractCandyDispatcher. The CandyConsumer has a different method for every candy type. To unify the call, we delegate the call to another class which dispatches the candy to the consumer. The AbstractCandyDispatcher has the abstract method eat. Every candy type gets an own dispatcher class, which calls the right method for the consumer. We plan to create the dispatchers dynamically. For this we create the method destruct to free the memory again, after dispatching. The class also provides the possibility to check if a dispatch is possible. This is done by checking the amount and a valid consumer reference. This check will be helpful for the concrete dispatchers.
We create folders to organize the candy dispatchers and create the AbstractCandyDispatcher class. After we created it, we add the Enable Dynamic Creation attribute to it. Next, we add the abstract method eat. In here we declare the consumer as input variable. The consumer is a reference to the AbstractCandyConsumer class. As other input we declare the variable amount of type CandyAmountInGram. As we said before, we want to create the dispatcher dynamically. The next method we create will free the memory again after dispatching. We call it destruct. It returns a pointer to the AbstractCandyDispatcher. In the method we declare a constant variable. We call it null of types word as value we assign 0. It is a null pointer as return value. In the implementation part we add the code to free the memory.
The delete frees the memory, but the if expression makes sure to free the memory only if it was dynamically created.
The last method we add is protected and called eat candies is impossible. Its return value is a bool. As we explained before, we will use it to test the parameters. It returns true if at least one of the parameters is invalid, and returns false if all parameters are valid. As inputs we declare consumer, a reference to AbstractCandyConsumer. This is the consumer who eats the candy. And amount of type CandyAmountInGram. To test the parameters we implement the following code.
The next thing we will do is to add concrete dispatchers for all candy types. Let's do the first two together. Our first dispatcher is for the candy bars, and it extends our AbstractCandyDispatcher. In the implementation part we add the Enable Dynamic Creation attribute, because it should be created dynamically. In the eat method we fill the implementation part. If our test methods eat candies is impossible returns true, which means that at least one of the parameters is invalid, the method returns early, without dispatching any candy. If everything is fine, the method dispatches candy bars to the consumer. The next dispatcher we create dispatches candy corn. We extend AbstractCandyDispatcher again and add the enabled dynamic creation attribute. We copy the code of our CandyBarDispatcher eat method and paste it in the eat method of the candy corn dispatcher. We change eat candy bars into eat candy corn. We repeat this for all candy types, until they all have a dispatcher.
We remove the warning pragma in the declaration part of the eat methods.
At the end we remove the Enable Dynamic Creation attribute out of our AbstractCandyDispatcher, to prevent the generation of an abstract class with new.
The next thing we will do is to create a factory class for the creation of new dispatchers according to the candy type. We call it CandyDispatcherFactory and add the access specifier final to it.
Now we add a method to it with a pointer to the AbstractCandyDispatcher class.
This method creates a new dispatcher instance for a given candy type. The candy type must be a pure candy type. As input we need a candy type, that's why we create an input variable with the name candy type, and of course it is of type candy type. In the var section we declare now a pointer to the dispatchers for each candy type.
We do this because the new operator we will use in a minute requires a strictly typed pointer. At the end we declare a pointer to the AbstractCandyDispatcher and assign 0, simply call it dispatcher. This is the return value. In the implementation part we start with setting getNewCandyDispatcher to 0. We go on with a case instruction, case candy type of. The first two types we do together again. CandyTypes.CandyBars. CandyBarDelegator equals new CandyBarDispatcher. GetNewCandyDispatcher equals CandyBarDelegator. CandyTypes.CandyCorn. CandyCornDelegator equals new CandyCornDispatcher. GetNewCandyDispatcher equals CandyCornDelegator. After we implemented the creation for every candy type case, we implement an else with a return instruction.
Let's have a look at our suite diagram again, especially at the AbstractCandy class. Maybe you notice that it is not complete yet and that in the diagram, it extends the AnyToArg converter. This is the first thing we will do now. We write extends AnyToArgConverter. Now we will do some more changes and add more functionality to the class. We start with creating a folder and call it log. In here we add a method that we call log_CandyConsume. This method writes an ADS log message if a consumer was eating a concrete candy instance. The message contains the consumer name, the amount, and the satisfaction level of the consumer after the consume. As access specifier, we select protected. We declare an input variable. We use a reference to the AbstractCandyConsumer, the name of it is consumer. Because it is the consumer who eats the candy. In the var section we declare a string formatter of type tc2utilities.fb format string.
We use the format string FB because, as we said at the beginning, it's easier to use than the concatenation hell. Next we declare a variable called ConsumerName of type ConsumerName, because we need a variable and not a property for the format string FB. And another variable called Satisfaction, because of the same reason. It is of type SatisfactionLevelInProcent. In the implementation part we assign the input consumer.levelOfSatisfaction to our satisfaction variable. And the input consumer.name to our ConsumerName variable. Now we use the string formatter. S-format is the string we want to be displayed in our ADS string. We write %s was eating %d grams %s. The satisfaction level of %s is now %d%. The percent signs will be replaced with the arguments that we define now. To make an ADS log we use the function tc2system.ads_logstr. If you call the function it issues a message box holding a text you can define on the screen and an entry into the system's log is written. It has three inputs. Message control mask, this is the control mask which determines the type and effect of the message output. Message fmtstr, contains the message to be issued. strarg, contains the string to be inserted in the message. As message type we assign tc2system.ads_log message type hint. To the message fmtstr input we assign %s. And as string we assign the output of the string formatter.
Now we do some declaration in the AbstractCandy FB. We add a variable called dispatcher. It is a pointer to AbstractCandyDispatcher and add the attribute nocopy to the class. We use a pointer to a pointer because it is more iterable. The attribute nocopy is important for online changes to avoid exceptions. For creating the dispatchers dynamically, we also add the object DispatcherFactory of CandyDispatcherFactory to the class. And add the attribute hide to it. Next we add the number of types variable of type usant to the class, to store how many types the candy has. For example, a Snickers is a candy bar, a chocolate candy and a caramel candy. In this example the number of types is 3. We add the private method addNewDispatcher to create a dispatcher for a given candy type. As var_in we declare CandyType. This is the candy type which will add the new dispatcher. In the var section we declare a pointer to the abstract dispatcher. We use the pointer to store the abstract pointer in the array. A pointer to a pointer. We call it dispatcher. Next we declare the array. And call it dispatchers. It is a pointer to an X word. In this method you can see how to make a iterable array with candy dispatchers. For this we use the pointer to AbstractCandyDispatcher variable. The method adds a dispatcher for a specific candy type to the concrete candy. It's possible that a concrete candy has more than one specific candy type. For example, a Snickers is a candy bar, a caramel candy and chocolate candy. Since the consumer has for every candy type an extra method to call, the class AbstractCandy uses dispatcher classes to simplify it. Since it is not possible to create an array of references to AbstractCandyDispatcher, the dispatcher is a pointer to make it iterable. Now we add a private method to the class and call it freeDispatchers. It will destruct the dynamically created dispatchers and free the memory again. In the method we will work with a for loop. For the loop we need a counter variable which we declare now, current dispatcher of type useInt. The memory is allocated as X word, that's why an X word pointer is required to free it again. We call it dispatchers. In the implementation part we start with to return instructions. If number of types or dispatcher is less than or equal 0, the return is executed. Next we use a for loop. For current dispatcher equals 0 to this number of types minus 1 do. This dispatcher current dispatcher dot destruct. End for. This number of types equals 0. Dispatchers equals this dispatcher. Delete dispatchers. This dispatcher equals 0. Now everything is set to 0 and the memory is free.
We go back to the AbstractCandy FB. Add the attribute CalAfterInIt to the class. This attribute causes a method to be called implicitly after the initialization of a function block instance. The method will be called after the initial assignments have been processed and before the tasks of a PLC project have been started. Because of performance reasons we have to add it not only to the method but also to the FB. We use it because the class doesn't know what type of candy it gets when the FB init of it is called. Don't worry. We will explain in a minute what this FB inits and FB exits are.
But first we add another method, yipa. The initializeDispatchers method. It creates the dispatchers dynamically after all FB inits are done. So this method needs the attribute CalAfterInIt.
In the method we will use another for loop. This for loop needs a counter variable for binary counting. We call the variable current type of CandyTypes. Next we declare one variable with binary candy types from FB init. My candy type of CandyTypes and initialize it with this .CandyType. At first we call the freeDispatchers method. If my candy type is less than or equals 0, a return is executed. We go on with the for loop. For each type we check if it is contained in my candy type. If so, we add a dispatcher for it and remove it from myCandyType. If that was the last type remaining in myCandyType, we return early.
The next method we create is the destruct method. Its return type is a pointer to AbstractCandy. And it is protected. As var constant we declare null of type X word. This is the value for a null pointer. This method frees the memory of an abstract candy if the candy was created dynamically. The method has no effect if the candy was not created dynamically. It returns a null pointer if it frees the memory and a pointer to itself if it has not freed the memory. The method simplifies the destruction of a candy object because it does not require a query pointer. To do so, we implement the following code. The next method calls the eatCandyType methods of the CandyConsumer and it destructs the candy object. We name it eatMe and as return type we select a pointer to AbstractCandy. As input variable we need a CandyConsumer, who eats the candy. We call it consumer. It is a reference to AbstractCandyConsumer. As variable we declare I, an index for another for loop. We assign a this pointer to eatMe. Next two return instructions. Return if consumer is no valid reference. Return if number of types is smaller or equals 0. Next the for loop. For I equals 0 to this number of types minus 1, do this dot dispatcher, I dot eat, consumer, this dot amount slash this number of types, end for. This dot log candy consume, consumer. eatMe equals this dot destruct. As you can see, the method calls the eat method with the amount for the candy consumer, writes the log message and destroys itself. The last method we add to the class is the fbExit method. And finally we will talk about fbInit, fbreinit, fbExit, and the magical call after init. The methods that control the lifecycle of function blocks in TwinCAT. We'll break them down, talk about inheritance behavior, and explain how these methods work in different operating cases like first download, new download, and online change. The fbInit method is used to initialize your function block. It's automatically called when a function block is created or reloaded. This method takes two parameters. binit retains, true if retain variables, means variables that keep their value across reboots, need to be initialized, used in warm and cold starts. bin copy code, true if the function block is being moved to the copy code, this happens during an online change.
In simpler terms, fbInit is like setting up the function block before it starts doing its job, making sure everything is in the right state.
Then there is the fbreinit. This one is for reinitializing the function block state after a memory shift, like during an online change. fbreinit is called after the old function block has been copied to the new memory location.
If you're using inheritance, you need to call dereferenced super.fbreinit in your derived function blocks to ensure the base class reinitializes correctly. This method resets variables or informs other parts of the project that the memory location has changed.
The next method is the fbExit method. It is responsible for cleaning up the function block before it's deleted or reinitialized. It's called when the function block is being removed from memory, like during a new download or an online change.
This method is where you can release external resources like sockets or files, or free up dynamically allocated memory with delete. In the context of inheritance, the base class's fbExit is automatically called after the derived class's fbExit.
We already used the attribute call after init before. It is a special method marked with attribute call after init. It's called after fbInit but before the function block begins its first task cycle. It ensures that external initial assignments, like variables initialized directly in the instance declaration, are fully processed.
Yep, it's useful when you want to react to user-specified values that are assigned externally to the function block. Think of it as a post-initialization step.
Now let's talk about how these methods behave in inheritance scenarios. When a derived function block, child, inherits from a base function block, parent, these methods follow a specific call order. fbInit, the base class's fbInit is called first, followed by the derived class's fbInit. This ensures that the parent's initialization logic is executed before the child's. fbExit, the reverse happens here. The derived class's fbExit is called first, followed by the base class's fbExit. This ensures that the child's cleanup happens before the parent's. fbReinit, if you want to reinitialize the base class's implementation, you need to call super_fbreinit explicitly in the derived class.
Now let's dive into how these methods behave depending on what's happening in your system. The three main cases are first download, new download, and online change. Operating case 1, first download. What happens when you download the PLC project to a brand new controller? Method calls. fbInit is called after the function block is created. External assignments, like variables set in the declaration, are processed after fbInit. If callAfterInit is used, it runs after external assignments.
This is the most straightforward case. Everything gets initialized from scratch, and any values assigned externally are applied after fbInit. Operating case 2, new download. What happens when you overwrite an existing project with a new one? Method calls. fbExit is called first to clean up the old instance. Then, fbInit runs for the new instance, followed by external assignments and callAfterInit.
It's like a full refresh. The old project's function blocks are cleaned up using fbExit, and the new ones are set up with fbInit. Operating case 3, online change. What happens when you make live changes to the PLC project? Method calls. If code changes only, no declaration changes, no fbInit, fbExit, or fbReinit calls. If declaration changes, like adding/removing variables, fbExit is called on the old instance. fbInit is called on the new instance, followed by external assignments. fbReinit is called to reset the new instance.
During an online change, if you modify the declaration part of a function block, TwinCAT will replace the old instance with a new one, and that's when fbExit, fbInit, and fbReinit come into play.
This is the trickiest case because you have to handle the copying of function block data between the old and new instances, and ensure memory pointers and other external resources are correctly reinitialized.
Let's have a look at the sample call order for derived function blocks. Let's say we have 3 function blocks: foo, the base class. Foobar inherits from foo. Foobarbaz inherits from foobar.
When we create an instance of foobarbaz, here's what happens in an online change scenario with declaration changes.
As you can see, exits are called in reverse order, and inits happen from the base up. Rainit calls are optional but should be included if the base class needs to reset after the online change.
So there you have it. FBinit, FBigsit, and FBrainit are all about managing the lifecycle of function blocks across different operating cases. Use them wisely, especially when working with inheritance or online changes.
And remember, CalafterInit is your go-to when you need to handle external initializations after the function block is created. With these tools in hand, you've got full control over your object's lifecycle. Back to our FB exit in the project. We need the method to free the memory of the CandyDispatcher again. In the implementation part we write this.freeDispatchers. Now the fun starts. We create the concrete Candy classes. Amount, name and CandyType is initialized in the FBinit. Let's do the first two together. First, we create the concrete Candy class, which extends the AbstractCandy class. Each of the concrete Candy classes has the attribute call after init, to make the creation of the dispatchers possible. And also the attribute enable dynamic creation, to make it easier for us with the Candy machine later. The Candy can be consumed by any CandyConsumer. It supports dynamic creation. Furthermore, it calls the method AbstractCandy.initializeDispatchers after FBinit. Each of the concrete classes has a FBinit method to define the properties of it. In its implementation part we assign the concrete amount, its concrete name and its candy types. We do this for every concrete candy. We will speed up the process a little. On the right side you can see the values for each class.
At this point, we will make a cut.
In the next part, we will create the Candy machines and get the entire program running.
So, take a little break and enjoy your favorite candy in the meantime.